Okay, let's continue the lecture. Okay, this topic is about the exponential coordinate for rigid body motion. Actually, in the previous lectures, we have introduced the concept of exponential coordinate for rotation. It will be extended to the rigid body case. So, in this section, we will define matrix exponential and the matrix logarithm to find out the exponential coordinate for rigid body motion. In the previous lectures, for given matrix form of rotation axis, if we take the matrix exponential, then we will get the rotation matrix. On the contrary, if we take the matrix logarithm to the rotation matrix, then we will get the matrix form of rotation axis times rotational angle. From here, we can extract the exponential coordinate of omega theta. Okay, by analogy to the exponential coordinate omega theta for rotation, let's define the six-dimensional exponential coordinate of the homogeneous transformation will be denoted by the S theta in R6 space. In here, theta will be defined as a distance that must be the travel along the screw axis to take the frame from the origin to the homogeneous transform. In here, non-zero omega, if your rigid body has the rotational motion, at that time the screw axis will have unit magnitude of rotational motion. In here, theta corresponds to the angle of rotation about the screw axis. On the other hand, if we have the pure translational motion, at that time the omega will be 0. In here, screw axis will have the unit magnitude of linear velocity. So theta will be corresponding to the linear distance traveled along the screw axis. So screw axis contains two kinds of concepts, rotational motion and translational motion. Okay, for given screw axis matrix form, if you take the matrix exponential, then you will get the homogeneous transformation. On the other hand, if you take the matrix logarithm to the homogeneous transform, then we will get the matrix form of a screw axis and the rotation angle or distance traveled along with the rotation axis. Okay, so we have the very similar concept between the rotation and the homogeneous transformation. Okay, let's expand the matrix exponential in the series form E2 S theta. Maybe you know the S implies this matrix. It defined in the 4x4 matrix, but it has the 6 independent elements like this matrix form of omega and V. Okay, this will be applied to here and here and here. It's very easy to obtain the S squared by multiplying the same things each other. Then we have this equation. S cube can be obtained like this. We have some rule. We can estimate S2n will be the omega n and omega n minus 1 times v, 0, 0. So this will be applied to the general form of this equation. Then we have 3x3 rotation and 3x1 linear velocity and 3x0 and 1. Okay, in the previous lecture, we have defined this series expansion is as a e2 omega theta for representation of a rotation matrix. The remaining terms will be this one. Okay, let's extracting the v. V is the vector, so let's remove this part, and the remaining part is defined as the g here. Okay, the first term is the I theta, second term is the omega theta square over 2 factorial, and then this is repeated like this. In here, you know that in the previous lectures, omega cube will be the minus omega, and the omega fourth order will be the minus omega square, omega fifth order will be the omega. So this will be applied to here. This is equal to minus omega, this is equal to minus omega square. Let's collect this one and this one. Then we have this equation. One more, if we have this sequence, we have this equation. In here, we can apply the sine and cosine definition. So it must be 1 minus cosine theta. It is equal to theta minus sine theta. So it's very easy to obtain the g theta using the theta and omega. So the g is applied to here, and then we can get the homogeneous transformation. Okay, for given square axis omega and v, in here's unit omega or unit v should be satisfied to be the square axis. For any distance or traveled along the axis, in the case of rotational motion, we can get the transformation, homogeneous transformation. On the other hand, if the omega is 0 and the unit magnitude of the v is applied, then we have this translational motion. Okay, let's take the matrix logarithm of rigid body motion. For given homogeneous transformation written by the RMP, we can always find the square axis S and the scalar theta traveled along with the square axis. Okay, for given transformation here, if you take the matrix logarithm, then we can get the matrix form of square axis and the scalar distance theta. So this is the 3 by 3 here and the 3 by 1 here and the 4 zeros here. This is called as matrix form of a square axis times distance is called as matrix logarithm of the homogeneous transformation. Okay, in the previous lecture, we have introduced algorithm 3.1 to extract the square rotational axis and rotational angle. In algorithm 3.2, we will introduce the concept, the similar concept of matrix logarithm. For given homogeneous transformation, in here, find a theta belonging to 0 to pi, a square axis S composed of the omega and v. In here, n is one of the unit magnitude of rotational velocity or linear velocity. In here, the vector S theta belonging to R6 comprise the exponential coordinate of the T homogeneous transformation, and the matrix form of the skew square axis times theta is the matrix logarithm of the t. Okay, we should differentiate the meaning of the s theta and s theta. It will belong to R6. It will belong to R4 by 4. It is called as matrix logarithm. This is called as exponential coordinate for rigid body motion. In here, if we have the unit identity matrix as a rotational rotation, at that time we have the 0 omega. So we have just only a translational motion. So V should be unit by dividing the magnitude of the linear velocity. So we have the distance travel by the magnitude of the p. Otherwise, the rigid body motion will contain the rotational velocity. So matrix logarithm to determine the omega, written as the SO3, and the theta for R. Actually, it is suggested in the algorithm 3.1. Okay, using the trace and the skew symmetry property. And then the remaining one is the V. V is obtained by the inverse matrix of the G times P. Okay, the G inverse is obtained like this equation. Actually, the proof of this one will be is left as an exercise. You have this is homework. Okay, homework number 2. Okay, let's take example 3.4. Assume that the rigid body motion is confined to the xy plane. The initial plane B and the final plane is the C. It can be represented by the SE3 matrix. Okay, let's take the fixed frame, and the initial plane is here. Okay, so if you describe TSB is obtained, maybe the position will be either 1 to 0. Maybe this is the 1, this is the 2 unit, and then rotational angle will be the 30 degrees. So we have the rotation matrix. Okay, the final description of the frame C. Okay, in here, maybe the position will be 2 unit and 1 unit. So you have the 2, 1, 0, and then the rotational angle will be the 60. So you have this rotation matrix. This is the initial, this is the final. So all the frame will be described using the space frame, fixed frame. So E2 S theta will act like operator. TSB will be the TSC, because this is the operator to change, to displace the transformation matrix. Okay, from here to here. Okay, the E2 S theta can be obtained, the TSC, TSB inverse. Okay, it's very easy to inverting this one, and then we will multiply to here. So E2 S theta is calculated using the MATLAB. We can get this equation. In here, this is the R, this is the P. Okay. From the exponential coordinate, exponential transform, we can extract the matrix logarithm first. For this distance traveled along the rotational axis can be obtained. Actually, the trace of the r minus 1 over 2, and then we take the arc cosine is equal to the rotational angle. So trace, by adding a 3 element, it will be 1 plus square root of 3. So minus 1, we have the square root of 3. So arc cosine square root of 3 over 2 will be equal to the 30 degree. It is corresponding to the 0.5236 radian, because the 1 radian is defined as the 1 pi over 180 degree. Okay, this is the first step. The second one is to find out the rotational axis from the rotation matrix. This rotation axis can be extracted from the rotation matrix R minus R transpose over 2 sine theta. We know the theta. Sine theta will be the 1 over 2. So we can get the 1. So the R minus R transpose will be this equation. By matching the skew symmetric form of rotational axis, we can get omega 3 is the 1, omega 2 is 0, omega 1 is 0. So we have it. Rotational axis. Okay, we know the G inverse matrix. So G inverse matrix like this. We know the theta and the omega hat here. So by applying this one and this one and like this, we can get this equation. And then P is this one, this vector. So this will be applied to here. Then the linear velocity of a square axis is obtained like this. By collecting the omega and v, we can get a 6-dimensional square axis, omega and v. It must be the square axis because the omega is the unit magnitude. By multiplying the distance traveled along with the square axis, this is the 30 degree. It means 0.5236. I'm not sure the radian value should be multiplied to obtain this exponential coordinate. So we can get it. It is called as exponential coordinate for rigid body motion. Actually, it can be obtained graphically here. Okay, let's consider. I'm sorry. Okay, here. Actually, this point is the square axis. Okay, here 1 radian per second is applied. At that time, the linear velocity of the fixed frame will be obtained. Omega s cross minus q. So if you write down the rotation angle, then we will get this linear velocity. So by collecting the rotational angle 0, 0, 1 and 3.367, 3.37 and 0, it will be the square axis. Okay, the rotational angle, actually this is the 30 degree, this is the 60 degree. It means that this is the 30 degree. So maybe the 0.52 radian is applied to here. Then we can get the exponential coordinate for the rigid body motion, this motion. Okay. Okay, the graphically we can get it. We can understand what happened in the rigid body motion. Okay, the last topic is about the wrench. Wrench is the dual form of a twist. So, in order to describe the wrench, we should specify the point. Okay, the coordinate-free point R is chosen, and then force vector is chosen like this. It is independent of the coordinate. This is the physical dimension. In order to describe the force and torque, we should attach the coordinate. At that time, the place vector, displacement vector RA appear. If we take the another coordinate, at that time the RB coordinate will be different from the RA. Actually, it depends on the coordinate, where the coordinate is. Okay, anyway, the linear force F acting on the rigid body at a point R. This is the coordinate independent variable. By defining the reference frame A, at that time the point R can be represented as a RA belonging to R3 space. And the linear force F can be represented as a FA. So the subscript will represent the coordinate frame. Okay, if you consider the force, this force will create the moment. Okay, the moment or torque value denoted by the MA is obtained R cross F. So moment or torque is defined as RA cross FA. Okay, we know two kinds of variable, linear force and moment. Both are dependent on where the coordinate is, where the frame is. So by collecting this 6 element, we can define the wrench. Wrench has the 6-dimensional special force. The first part will be the moment, and the latter part will be the linear force. Okay, so it has the 6 element. If you have the 0 force, at that time the pure moment appear. Wrench is the dual concept of the twist. So wrench and twist can be described in the A frame or B frame at the same wrench and the same twist. But the power, the V cross F implies the power. In the vector notation, V transpose F, because the power is a scalar variable belonging to just R space. The power is independent of the coordinate. It means the same force and same moment is appear if you take the different coordinate, but the power will be the same each other. So the VB transpose FB and the VA transpose FA should be equal each other. The power is independent of the coordinate. We know the VA is equal to VB. It can be matched using the adjoint map. Do you remember that? TAB. Okay, this concept is applied to here. Okay. By applying the transpose operators, the VB transpose appear front side and the adjoint map go to the lateral part. So this part will be equal to FB. So we can get the transpose of adjoint map between the length. Okay, given length F, represented in A frame, will be denoted by the FA. In the B frame, FB. Two representations are related by, okay, the FB is the adjoint map TAB transpose FA. On the other hand, FA is the adjoint map of TBA transpose FB. Okay, so adjoint transpose operator of adjoint map is used to relate the between two range. Okay. Okay, it will be the last example of this chapter. Okay, let's consider. This is the robot and the effector. The pulse torque sensor will be attached. Okay, pulse torque sensor will be attached to here, and then we have the coordinate x and f, x and y. This is the hand. This is the center of mass. Let's attach the x and y coordinate. The distance will be the L1. L1 is the 10 centimeter, 0.1 meter. And then the robot hand is grasping the F4. Okay, this is the center of mass. Let's attach the x and y coordinate denoted by A, XA, and ZA. The distance will be the L2, and then the gravity is going downward. Okay. What is the pulse and the torque measured by the 6-axis pulse torque sensor between the hand and the arm? Okay, the mass of apple 100 gram, mass of hand 500 gram, gravity is assumed as 10 meter per second square. L1 is the 10 centimeter, L2 15 centimeter. Where is F is attached to the pulse torque sensor, H is attached to the center mass of the hand, A is attached to the center mass of apple. Okay, the length on the hand here in H coordinate, maybe the gravity is affected like this. Okay, so the three moment value will be the 0 because the center mass is considered to account for the moment, so it will be 0. How about the pulse? The gravitational pulse is opposite to the YH. So 0, minus 5, and 0. Okay, length on the F4 in the A frame. The F4 is the 0.1 kilogram, so 10 times of gravity, 10 meter per second square gravity will be applied to here, and 1 Newton is appear in G direction. So 3 moment is 0 and the G direction 1 appears. This is the length of the, this is the FA. Okay, let's take the transformation matrix from the 3 coordinate. Okay, the transformation of the F relative to H. H is base coordinate in here. Let's read the F. XF is aligned to the XH, so 1, 0, 0. YH is aligned to the FF, so 1, 0, 1, 0. G is equal to the. And then this point can be led minus 10 centimeter x direction, so minus 0.100. The remaining 3 0 and 1 append. 1 is append to make the 4x4 matrix. On the other hand, TAF. Okay, let's read the XF in terms of the A coordinate. This is aligned to the XA, so 1, 0, 0. And Y will be the Y direction will be the inside the page. So this is equal to 0, 0, minus 1. The z-axis is minus y, so I'm sorry, the y-axis is the minus g, and the g-axis is equal to y-axis, so we have the 0, 1, 0. In here, this point can be led by the minus x direction, 0.25, so we have this equation. Okay, using this kind of setup, we can calculate the length applied to the post-hoc sensor. Okay, post-hoc sensor is obtained using the adjoint map transport of FH, so this map and the FA. So using the transformation, we can write down this is the R, this is the P, R, this is the R, this is the FH. One more. This is the R, this is the R, this is the P bracket, P bracket, and the R. So this is the FA. Actually, the transpose operator should be applied to produce the result. Then actually the pips element is remains. I think this part can appear as a result using the minus 5. So we have the third one and the fifth one, minus 5 times, and this is the sixth element, so this part will appear, the third one and the fifth one, third one and fifth one, so we can get this length in terms of post-hoc sensor frame. Okay, we have finished today's lecture. Okay, we have the two tables in here. It's very important. Rotation matrix and rigid body motions. Those are very similar concept, and the dimensions are different from each other. Rotation matrix will be corresponding to the homogeneous transformation. Okay, and the rotation axis to describe the exponential coordinate for rotation. It is extended to square axis as a 6-dimensional space. So using the rotation axis and the square axis, we can define the angular velocity and twist. Twist contains two kinds of velocity, linear velocity and angular velocity. And matrix form of twist is belong to SU3. The dimension of this one will be the 4x4 matrix. And R dot R inverse is the matrix form of the omega S. R inverse R dot is the matrix form of the omega B. The similar concept is obtained using the twist, body twist and special twist. In order to change the frame, coordinate frame, the adjoint map is used. Okay, and the exponential transformation, exponential matrix exponential will be the rotation. The matrix exponential of the etc. will be the homogeneous transformation. In here, so we have several equations. This is the G, okay? G inverse, you should know the G inverse matrix as well to obtain the linear velocity of linear velocity part of the twist, okay? Wow, you should memorize this property and this equation to understand next kinematics and dynamics, okay? Okay, you have the second homework about the chapter 3. Please solve and submit exercise 3.5, 6, 7, 14, 17, 18, 21, 22, 23, 24, 25, 39. The due date is the April 9th. Please upload it as a PDF form or email me including the attached file. If you have some questions, let me know what the problem is until the April 7th. Before then, if you let me know that, I will include the solving procedure in the next lecture.